Hi, welcome back to another podcast with Maria Lopez and
Michaela Nava.
on Ocean Overtime.
During Ocean Overtime, we will be discussing the atmospheric circulation and ocean circulation, and we're going to go into depth about what these two things are, and we're going to talk about their process within the Earth.
And we'll be also discussing the similarities and differences between atmosphere and ocean circulation. Go.
We are going to begin discussing atmospheric circulation.
Atmospheric circulation is important because it affects the weather in different regions of the Earth, and it affects how the air is circulated throughout the planet.
On average, this circulation corresponds to large-scale wind systems that's arranged in several east-west belts that encircle the Earth. In regards to that, I'm going to examine the ways that the oceans and the atmosphere interact with one another, like based on solar radiation, and I'm going to talk about how it influences the wind and the atmospheric circulation along with the climate zones and the weather. So to start, I'm going to go into depth about the Earth's heat budget, and this is basically the balance of outgoing heat that is coming on Earth. And also I'm going to discuss the solar energy. So solar energy reaches the Earth about 30%, and it's reflected back into space from the atmosphere, clouds, and the surface of the Earth. And half of the incoming solar radiation is being absorbed from land, and the ocean energy is heating up through the Earth's surface. So when it comes to heat, it's also known as conduction, and during conduction, it's like the transfer of heat. So the transfer of heat is directly contacted between the surface and the atmosphere. So conduction is represented from a small part of energy in which it transfers between the Earth and the atmosphere, which this equals about 7% of the incoming solar energy.
Okay, now I'm going to be talking how does the Earth circulation works. The Earth is separated into three different cells. The three cells that it's separated into is the Hartley, the mid-latitude, the polar, and the fertile cells. The Hartley cell is made by rising the air in the equator, and the fertile cell rises at 60 degrees and sinks at 30 degrees, and the polar cell is the cold air that rises as it moves from the poles. The Hartley cell are the low latitude overturning circulation that have air rising to the equator and sinking at roughly 30 latitude, and they are responsible for the trade winds in the tropical, and they control the latitude weather patterns in the world on Earth. And each one of these type of cells are in each atmosphere. The northern atmosphere and the southern atmosphere reflects on one another, with the equator being in the middle. And I also wanted to discuss how the atmosphere circulation works. Warm air rises towards the poles from the tropicals, and the warm air goes up north in the northern sphere, and warm air goes towards the south in the southern sphere, and the air cools and goes back down to the tropical, and it repeats again. I also wanted you guys to know that the polar is 60 to 90 degrees in north and south, in the north and south, and it's also in the Antarctica, Denmark, Alaska, and Russia. The fertile is 30 to 60 degrees north and south, and it's in the United States, Canada, and also Russia. And the Hartley is 0 to 0 to 30 degrees north and south is in the Sahara Desert, Brazil, and Mexico. Oh.
Go more into depth about the polar regions. So the poles reflect more solar energy than other parts of the Earth since the poles have higher albedo. And if you don't know what albedo is, it's a proportion of light that's reflected from a surface. So now that I talked about the poles, I'm going to begin talking about the wind patterns. So between the equator and 30 degrees are what we call trade winds. So polar winds also blow to the east, and between trade and polar winds there are westers lies, and low pressure is at the poles. So when it comes to the wind and climate, humidity comes from the warm air that's at the equator, and that's where it contains more water vapor. And in low pressure systems, it's associated with more rainfall. And then the areas within the Hadley cells are most commonly deserts, and they're deserts since most of the water's content is lost in the equatorial range. So due to that, it increases again at feral cells, and that leads to the formation of boreal forests. And then when that happens, it decreases again at the poles.
Since Michaela mentioned the deserts, I want to talk about how the cells affects the weather. In the hot desert, the air is sinking, creating high pressure, and is unable to form clouds and unable to create rain or shade in the desert. And the cells that I am referring to is the Hartley and the poloid and the furrowed cell, and that's how they affect the hot desert. Yeah. And it also could affect the equator by with rising air, creating low pressure, and it's gonna be really hot because the sun is like right over it, and it could also affect the clouds and like with the rain with the equator.
Now, with going more into depth about the atmospheric influences, the sun and the atmosphere, they both drive directly or indirectly almost all dynamical processes in the ocean. So, like sunlight, evaporation, sensible heating of the sea from cold winds and warm winds. So with the sensible heating, like we discussed with the heating, the winds allow the ocean surface circulation to work the way it does, and this allows the water to circulate throughout deep and shallow waters. So with this, it's the ocean's dominant heat source due to the ocean varying in temperature and the difference in heat, which causes the winds in the atmosphere to change as well. So the energy from the sun typically works with ocean currents to drive global winds, and they both win the power of the evaporation and the water. So when I talk about evaporation, as a water vapor, it's carried through the atmosphere, and it then becomes clouds and eventually rain. And the clouds that eventually turn into rain releases latent heat into the atmosphere. So when it releases latent heat into the atmosphere, the amount of clouds begins to increase. It helps retain more heat, which leads to evaporation and water vapor into the atmosphere, and it allows the cycle to keep continuing, and there is more heat that's developed
Since you got more knowledge on the atmosphere circulation, we will be moving on into the ocean circulation and discussing how it works and everything else.
So ocean circulation, it's a key regulator of climate, and by storing and transporting heat, carbon, nutrients, and fresh water all around the world. So complex and diverse mechanisms interact with one another to produce this circulation and ocean circulation. It can be conceptually divided into two main components. One being the fast and energetic wind that's driven this circulation, and then another which is a slow and large density driven circulation, which overall dominates the deep sea. So wind-driven circulation is by far the most dynamic. So blowing winds produces currents at the surface of the ocean. It's oriented at 90 degrees to its direction, and due to the Earth's rotation. So as a consequence, it can create zones of convergence or divergence of ocean currents at the point where they meet. Divergence of currents will typically create an upwelling phase, which is like the interior waters that reach the surface. And then it also will do a convergence, a downwelling phase, and that's like a surface waters where it sinks into the interior ocean. So they will be linking surface and interior waters. So like the slow and deep circulation is largely driven by water density and the temperature and salinity. So it acts on the ocean as a whole, and it has major influences on the abyssal properties, where wind-driven circulation, it has no effect. So, however, the circulation is slow and it's generating weak currents, so it might be difficult to observe. The large-scale circulation is relatively stable, though. At some very specific locations, like the northern Atlantic and around Antarctica, the surface waters, they become denser and they sink into depths. So densification can occur due to both cooling surface waters and an increase in salinity. The surface waters are pulled up to replace the sinking ones, and how waters upwell from depths to the surface is still unclear, but as I stated, the zones of divergence of water, they're critically important for the phenomena, but near seafloor turbulence also plays a major role. So these mechanisms are still poorly understood, and their spatial variability remains largely unknown, but the ocean circulation is sensitive to the global freshwater flux, and this is described as the difference between the evaporation, and it enhances salinity and decreases salinity as well. So global warming undoubtedly led to more ice melting in the poles, and due to this, it's the larger additions of fresh water in the ocean at high latitudes. So overall, generally, it's important to note that interactions between oceanic circulation and climate are poorly understood. More observations and increased understanding and reliable numerical models of oceanic circulation, they're needed for different space and time scales. Ocean currents, they're continuous, and they direct movements of ocean water that's generated by the forces that they're acting upon. So this means the flow, breaking waves, wind, the Coriolis force, the temperature and salinity differences, and tides can cause the gravitational pull of the moon and the sun. So the depth contours, shoreline configurations, and interaction with the other currents can influence a current's direction and its strength. So the currents of the ocean, it can flow for great distances, and together they create the great flow of the global belt, which plays a dominant part in determining the climate of many of the Earth's regions. For example, like the Gulf Stream, it makes Northwest Europe much more temperate than any other region at the same latitude. So another example could be like the Hawaiian Islands, where the climate is cooler than the tropical latitudes in which they're located, so due to the effect of the California current.
Okay, continuing off Michaela's talk right now. I want to talk about the two major currents in the ocean circulation: surface circulation and thermatic circulation, which is also known as surface currents and deep water currents. And surface currents makes up 10% of the water, and deep water currents makes up the other 90% in the water in the ocean. And the surface currents, they're in the upper 400 meters of the ocean, and the deep water currents, the deep water moves throughout and around the ocean basins. They are both controlled by water density and gravity. To continue in ocean currents, I mean, I mean, yeah, ocean currents. The surface. Okay, to continue. Surface currents are created by four things: the global wind pattern, the Earth and orbit, the Earth orbit and the rotation of the Earth, and the shape of the ocean basin, and the Earth's gravity. The global wind pattern is through the tides. They contribute to shore distant coastal currents, and the major surface ocean currents are created by the wind, and the wind drags the water with it, and it blows in any given direction. So lastly, I want to talk about how the ocean circulation works. It mostly also works with the gyres, and the main gyres is the North Atlantic, South Atlantic, North Pacific, South Pacific, and the Indian Ocean. And it moves clockwise in the northern hemisphere, and it moves counterclockwise in the southern hemisphere. And the water moves from the pole to the equator and back. And the cold and warm water is circulated through the gyres. So the cold water and the warm water in the ocean goes through the gyres. And okay, so the North Atlantic gyre it's formed by the northern equator current, and it flows to the Gulf Stream, and the waters warm, and it moves towards Europe, so it becomes cold. So the North Pacific gyres is the compound of the North Equator currents, and it brings warm water to Japan, and it flows to the North Pacific currents, moving to the east, Northern America, and becoming the California current. So the North Pacific gyres is the California currents, and the ones that we have right now, and it also bring warm waters to Japan. And the South Atlantic gyres is in the south currents, and it travels to Brazil, and the Brazil current brings in heat, so eventually it will turn into cold temperature or cold water. And the South Pacific gyres, it will become the Peru current, and will make it cold, and it will move up west of South America, and leaving it with warm temperature water. And lastly, I'm gonna it will go to the Indian Gyre. Um it's west of Australia and the ACC. It will bring the West Australia current will bring in cold water, and eventually will bring in warm water. Like throughout time, it will bring in warm water. So lastly, I'm going to talk about the connections between the atmosphere circulation and ocean circulation. So the ocean makes up 71% of the earth, and the ocean contains heat, and the ocean and atmosphere has an interconnection relationship that we'll be discussing in the last couple minutes of the podcast. The ocean circulation connection to the atmosphere is the ocean store heat that is transferred from the atmosphere, and it could affect the weather. Heat is pushed on land through the gyres and current movement. So the atmosphere, so the ocean stores heat to transfer to the atmosphere, and from that heat, it could affect the weather and pushes to the land, which stabilize global climate patterns. To continue, the wind atmosphere, not the wind atmosphere. Sorry about that. The atmosphere circulation connects to the ocean, also because the wind from the atmosphere helps push the currents to currents, and helps transfer and cold heat and cold in the ocean from the atmosphere. And I also wanted to talk about how um they both could affect global climate and like climate change, because it's affecting the weather. And yeah, so to sum up the similarities, it moves from the tropicals to the poles. It transfer heats and cold water. It transfer heats and cold into the ocean, and the circulation system always repeats. So they both repeat no matter what the circumstance. It could affect the weather, and it divides and affects the ocean, and the atmosphere affects the equator. Equator. So the atmosphere circulation is heat that moves towards the poles to the tropical, and the air in the tropical are warm and less denser. And the ocean circulation is different gyres in the ocean circulation created from water from the northern and south equator. And yeah, I'm pretty sure that covers up atmosphere circulation and ocean circulation. I don't know if Michaela wants to add anything about it.
Yes, Maria, you pretty much covered everything. Great job on that. That is the end. Thank you all for listening. I hope you got a really good take on what we discussed, and I hope that you gained knowledge, and maybe you can explain ocean circulation and explain it to somebody.
Okay, so that covers up SLO number 2 on atmosphere circulation and ocean circulation, and I hope you understood the similarities and differences between the two circulations systems, and I hope you could understand the inner relationships between the two, and how they are construction, and how they could affect the planet and the planet. So that concludes Ocean Overtime with Maria and Michaela. If you have any questions, you could always send us an email or comment below or anything.
Yes, thank you all for listening on our second podcast. This was really fun to just discuss everything. I hope you all got a good take on what each of the topics are. Thank you very much.
Okay, so see you next time on Ocean Overtime with Maria and Michaela. Bye.